Welcome back for some more reinforced concrete design. In this lecture, we will look at how to design a doubly reinforced section, and we'll also go over an example. We start with a balanced singly reinforced concrete section. In this section, both tension steel and compression concrete fail at the same time. Concrete fails in a brittle manner. To assure ductile failure, Eurocode 2 limits the height of the concrete compression zone at the ultimate limit state to 0.45 of the section effective depth D. If the rectangular stress block method is used for modelling stress distribution of compressed concrete, the actual height of compressed concrete is 0.8 times x. Application of the discussed limit to x leads to the depth of stressed concrete equaling to 0.36 d. Since the stress in the concrete is uniform and equal to its design compressive strength, the force in the concrete stress block can be found as 0.204 times FCK times B times D, where FCK is the characteristic compression strength of concrete. The tension force in steel equals to the area of steel multiplied by its design yielding strength, 0.87 FYK. As a result, there are two forces acting on the section considered. For a designed reinforced concrete structure to remain in equilibrium, each part of its cross-section has to remain in equilibrium. The planar force systems shown on the top right corner should satisfy three equilibrium equations: the sum of forces in the vertical and horizontal directions, and the sum of moments. The sum of forces in the vertical direction is satisfied automatically due to the absence of vertical forces. The equilibrium in the horizontal direction is satisfied when the compression force in concrete equals the tension force in steel. The required area of reinforcement in the balanced section can be found from this condition using the following expression. In design, the amount of reinforcement in different sections can be compared using the reinforcement ratio, which is the ratio of the area of steel to the area of concrete in the section. In the case of a balanced section, the reinforcement ratio becomes 23.4 times the ratio between the characteristic strength of concrete and steel. The lever arm in the balanced section equals to 0.82 times D. From the equilibrium of moments in the balanced section, the maximum moment such a section can carry equals to 0.168 FCK times B times D squared, which means that the limit for the parameter K is 0.168. You might sometimes see this in other books rounded down to 0.167. So the design procedures developed for a singly reinforced concrete section cannot be used when the moment applied on the section is larger than the limit moment. The latter means that the parameter K is larger than the limit of 0.168. In this case, the expression for parameter K suggests that to resolve the situation, we can increase the size of the section or the strength of concrete. However, these solutions are not always acceptable. For example, there might be some headroom constraints. The alternative solution is to use compression reinforcement in the section. A section with compression reinforcement is called doubly reinforced. Let's consider the design model of a doubly reinforced section. We start off with a model of the singly reinforced balanced section. In this section, the force couple C and T can carry the moment M limit, which is smaller than the applied moment. To increase the moment carrying capacity of the section, an additional force couple is required. The additional force couple, delta C and delta T, is introduced by incorporating two additional sets of steel bars at the top and bottom of the section. This force couple can carry the additional moment delta M, which is above the moment M limit. As a result, one set of bars is in tension and located at the level of the bottom bars in the balanced section, while the other set is in compression and located in the concrete compression zone close to the top surface. In the doubly reinforced section, compression steel is added to take some of the compressive force required. Additional tension steel is added to balance extra compressive force. The X to D ratio is limited to 0.45, but can be smaller for moment redistributions larger than 15%. Part of the doubly reinforced section is the singly reinforced balanced section, which remains under-reinforced. Let us now consider the model of the doubly reinforced section. We will use the rectangular stress block method for stress distribution in the compressed concrete. Here you can see a typical doubly reinforced section with the bottom steel AS and the top steel AS tag. The top bars are located at a distance d tag from the top surface of the section. The linear distribution of strain and the location of forces in the section are shown here. The model of the doubly reinforced section has two equilibrium conditions: equilibrium of forces in the horizontal direction and equilibrium of moments. In the equilibrium of forces, the tension force in steel should balance the compression forces in both the concrete and top steel. This condition leads to the following equation with two unknowns, which are the areas of the top and bottom steels. The moment carrying capacity of the section can be found from the equilibrium of moments around the tension steel and is combined from the contributions from the compression forces in concrete and the top steel. The expression for the moment takes the following form. When the applied bending moment is known, the area of the compression steel can be found as follows. Now the area of the bottom steel can be found from the equation obtained from the equilibrium of forces that we saw in the previous slide. In the expression for the compression steel, the first term represents the part of the bottom tension steel required to balance the compression force in the concrete and carry M limit. The second term is needed to balance the top compression steel and carry the remaining moment. The expressions for AS tag and AS can be rearranged in the following forms using the parameters K and K limit. The yielding strain in concrete is higher than in steel by more than 60%. Given the linear distribution of strain adopted in the doubly reinforced concrete section model, the position of the compression steel relative to the top side of the compressed part of the section defines whether or not the steel has yielded. The strain in the top steel can be found from the linear distribution of strain through the section depth using similarity of two triangles. In the strain distribution shown on the right-hand side, the first triangle has the legs epsilon Cu and X, and the second triangle has the legs epsilon SC and X minus D tag. The ratio between the depth and strain in the top steel can be found from the equality of leg ratios. For the top steel to yield, its depth in the section should not be larger than 0.38 times the depth of the compressed concrete. If we use the Eurocode 2 limit for the value of X, we obtain the following condition: that d tag over d has to be smaller than 0.171, which assures that the top steel has yielded. The maximum depth of top steel in the section at which the steel will have yielded can also be found using stresses instead of strains. On the one hand, the strain in the top steel can be found from the similarity of triangles. On the other hand, the strain in the top steel can be found using the steel stress and elastic modulus. Equating these two expressions and rearranging leads to the following relationship between Fyk, X, and D tag. After multiplication of numbers, this relationship takes the following form. Now the limit for the depth of top steel can be defined, and if D tag is smaller than X, 1 minus Fyk over 800, steel yields. Otherwise the top steel does not yield, and its stress can be calculated as 700 open brackets 1 minus D tag over X. An alternative condition is that when D tag over D is bigger than 0.171, or alternatively D tag over X is bigger than 0.38, the compression steel does not yield. In this case, the stress in the top steel will depend on the position of the bars in the section. The expressions for the top and bottom steel areas are updated in the following way to reflect the lower force carried by the top steel. The design of a doubly reinforced concrete section starts with the evaluation of the parameter K limit for the selected redistribution level. Next, the limit value of the bending moment and the corresponding area of bottom tension steel are calculated based on the value of K limit. From the limit of the X to D ratio, the depth of concrete in compression can be calculated. The area at the top compression steel is calculated for the additional moment M minus M limit, depending on the yielding condition. The area of the bottom tension steel is updated by summing the steel area required to balance the force in the compressed concrete, and the steel area required to balance the top compression steel. The reinforcement provided is checked for maximum steel area in tension and compression as allowed by Eurocode 2, using a reinforcement ratio limit of 4% of the concrete section area. We will now demonstrate the application of these design equations with an example. Consider a beam spanning 6 meters with a cross-section 300 mm wide and 450 mm deep. The beam carries a moment of 275 kN. The yielding strength of steel, Fyk, is 500 megapascals, while the compression strength of concrete, FCK, is 30 megapascals. We need to design the beam reinforcement, assuming 15% redistribution of bending moments. We start the design by calculating the depths of the bottom and top reinforcing steel. If we do that, we find that D equals 400 millimeters and D tag equals 50. We already stated that the limit for the parameter K is 0.168 for 15% redistribution, as we can see here in this table. We can now calculate the limiting moment, and the moment that will correspond to that K limit is 241.9 kilonewton meters. We can now find the depth to the neutral axis. The limit value for the depth of the neutral axis is 0.45 times the effective depth of the section, which equals, in our case, to 180 millimeters. Next, we can check whether the top steel yields using the following inequality. Since D tag equals 50 millimeters and is smaller than 67.5 millimeters, the top steel will have yielded. Therefore, we can use the formula on the slide to find the area of the top steel. And using that formula to calculate the area of top steel, we get 218 millimeters square. The lever arm Z that corresponds to that limit value of K works out as 325 millimeters. The area of the bottom steel AS required to carry the limiting moment is found using this formula, and if we calculate everything, we find that it is 1,712 millimeters square. The total area of the steel at the bottom of the section is the sum of the tension steel AS and the compression steel ASC. If we calculate it, it works out as equal to 1,930 millimeters square. We can now select the top steel, and for that we can see from the tables we've seen before that we can take 2 bars of 12 millimeter diameter, and that will give us an area of 227 millimeters square. For the bottom steel, we can take 4 bars with 25 millimeter diameter each, and that gives us an area of 1,964 millimeters square. We can now calculate the spacing between the 4 bottom bars using this formula. Here, in this example, the minimum concrete cover equals 25 millimeters due to bond requirement. The extra cover for deviation is 10 millimeters, and the clear spacing works out as 43 millimeters. Obviously, we should check that to ensure that the spacing is not less than the minimum required. We'll discuss that on the next slide. The clear distance between bars should not be less than the maximum bar size, 20 millimeters, or the maximum aggregate size plus 5 millimeters. These limitations assure that there will be adequate flow of concrete around the reinforcement during construction. Assuming that we have a maximum aggregate size of 20 millimeters, the clear distance between bars should not be less than 25 millimeters. Therefore, the 43 millimeter spacing that we obtained in our example satisfies this requirement. Join me next time for some more reinforced concrete design, where we discuss how to analyse flanged reinforced concrete sections.